Hi everybody, welcome back to my channel, and in this video we are going to be looking at a piecewise function. We're going to start off with this example here, f of x is equal to that piecewise function there. This is going to be example 1 in a series of videos. So I'm going to go through a few more examples in separate videos and just link them in a playlist. And in this example we're going to do a few things with this piecewise function. We're going to do some piecewise evaluation where we're plugging in different x values and getting out the function value. We're also going to go over graphing this piecewise function, and once we graph it, we're going to talk about the domain and the range, and then we'll take a look at finding the intercepts of this piecewise function. So the sheet that I'll be working off of, a blank note sheet, if you want to follow along and take notes with me in the video, you can check the description of this video and go print out this note sheet. It's linked on my website. And let's get started. So if you're completely new to piecewise functions, just looking at that function here can be a little bit overwhelming. Like, why does it have two pieces? What do these inequalities mean? So if you're completely new to piecewise functions, I just want to give you an introduction of what's going on in this function. So I'm going to head over to desmos.com and I'm going to graph the function and we'll take a look at it. So our piecewise function in this problem had two pieces. Both pieces were the equations of lines. I'll put a picture up of the equations right here. And these are what they are, these two equations here. I haven't put the inequalities in yet to graph them, but I'm just going to turn one equation on. So this is what the graph of that first piece looks like, negative 3x minus 4. I'll turn that off, and this is what the graph of the second equation looks like. Y is equal to 2x minus 1. Okay, so we have both of these graphs, but we have them going on in the same function. So I'm going to turn both of them on right now. Just looking at this graph right now, that graph is clearly not the graph of a function, as it is, because functions pass the vertical line test. And I can start putting in some vertical lines, like say even at x is equal to negative 2, and it's going to touch that graph more than once. So I need to consider those inequalities that we had going on in that function. Now, in the first piece of the function, we had the inequality that x was less than or equal to 1. So you see how that chopped off a piece of the red graph? Without that inequality, we had the entire red graph. When I take this away, we had the entire red graph. But once I put that inequality back, it chops off a piece in that bottom right corner. Now I'm also going to put the piece of the inequality that we had for the second piece, which was that x is greater than 1. You see how that chops off a piece of the blue graph? This is what the entire blue graph looks like. And now this is what the new blue graph looks like with that restriction on x. And notice that now these graphs do not overlap each other vertically. If I start drawing in vertical lines, they're only going to touch that graph one time. So now I really do have a function. So we have the red line coming in that stops at 1, only exists when x is less than or equal to 1. And then we have the blue graph that comes in right when x is 1 and goes on forever in the right direction when x is greater than 1. So now that we've seen an example of what that graph looks like, now let's go and do some things on that note sheet. The first thing we want to do is some function evaluation, some piecewise function evaluation. So we have these three different values. Let's start with the first one, f of 2. So this is asking us what is the y value that we get out of the function when we plug in 2 for x. So this little 2 on the inside of the parentheses represents an x value. Now when we are trying to decide how to plug that into the function, we have to figure out which piece of the function are we going to be using. Are we going to be using the first piece, that's the negative 3x minus 4 when x is less than or equal to 1? Or are we going to be using the second piece, the 2x minus 1 when x is greater than 1? Well, think about what our x value is. Our x value is 2. Which piece does that fall into, the red piece or the blue piece? It falls into the blue piece because 2 is greater than 1. So to evaluate this, I'm going to use piece 2. So I'm numbering my pieces. I'll call that piece 2, and I'll call the first piece piece 1. So this x value of 2 is getting plugged into the 2x minus 1. So instead of 2x minus 1, I'm replacing the x with the 2 that we're plugging in to give us 4 minus 1, which is 3. So the function value of this function when x is 2 is 3. Now let's go on to the second problem. We have f of 1. This time we want to plug in 1 as x for this function. So again, we need to decide which piece of the function are we going to use. Are we going to use the first piece in red or the second piece in blue? Well, our x value of 1 here, that's also showing up in those inequalities there. But it's only the first inequality that says x is less than or equal to 1 that includes 1. That second inequality just says x has to be bigger than 1, and 1 isn't bigger than 1, it is equal to 1. So to evaluate that second problem, we are going to use piece 1. We're going to use the first piece of the function. So the x value of 1 is getting plugged into the x from the first piece. So we have negative 3 times 1 minus 4, which gives us negative 3 minus 4, which is negative 7. Now we're on to our last problem in the piecewise evaluation part, f of negative 4. We want to plug the x value of negative 4 into this function. So we have to decide which piece do we use, the first piece that works when x values are less than or equal to 1, or the second piece that works when x values are greater than 1. That is, negative 4 is less than 1. So that falls into the first piece. So we're going to use piece 1 to evaluate this. So I'm going to take that x value of negative 4 and I'm going to plug it into the x from piece 1. So it is now negative 3 times negative 4 minus 4, which gives us a positive 12 minus 4, which is 8. So we have our three answers for those. Notice that for each of those problems, which piece of the function we used depended on the x value that was on the inside of the parentheses and which piece of the function that x value fell into. Also notice that under no circumstances did we plug these x values into both pieces. So sometimes when I'm grading papers on piecewise functions, I'll see students plugging the x value into the red piece and the blue piece. That's always wrong. Always, always, always. That violates the vertical line test. That's always wrong. When you're doing piecewise evaluation, there is only one piece of the function that you could possibly use. So that takes care of our first part on piecewise evaluation. So now we are going to talk about how to graph this piecewise function. So before we even got started with the first part, I went ahead and had pulled up this graph on Desmos. So we know what we're expecting to see. We're expecting to see something like this, but I want to talk about how to get this graph just on your own, if you're not allowed to use a graphing calculator or you're not allowed to use some kind of internet graphing tool. So how I like to handle graphing piecewise functions is I again break the function up into two separate pieces. So I have a first piece, that negative 3x minus 4 when x is less than or equal to 1, and I'm going to make a table for that piece. But in the table for that piece, I can only plug in x values that are less than or equal to 1. And I'll be plugging them into the negative 3x minus 4. And then I'll make a separate second table for the second piece where I will be plugging in x values that are now greater than 1, and I'll be plugging them into 2x minus 1. Okay. So I have my two separate tables set up, and more importantly, I have the conditions for my two separate tables. So for instance, in that first table, you cannot start off plugging in 2. You could not plug in 2 because 2 is not smaller than 1. That first table can only take x values that are less than or equal to 1. Very important part of graphing piecewise functions, very common mistake that I see people make. If there is a number that shows up in the restriction for your piece, you need to put that number in the table. So I'm definitely going to put 1 in the first table because it shows up in the restriction in that inequality, and I'm also definitely going to put 1 in the second table because it shows up in the inequality. Now at this point in class, some of my students start freaking out. Hey, you cannot plug 1 into this table because this says x is greater than 1. I promise you can. I promise you should. Let's deal with the first table, and then I'll talk about why we put that in the second table. So x is less than or equal to 1. I like to get at least 3 x values that are going on. Technically with a line, you only need 2, but I'm going to plug in just a couple more values. I'll use 0 because 0 is smaller than 1, and I'll just pick another random number. I'll choose negative 1. I like to choose smaller values just so it'll fit on a graph. And a lot of times I get the question, where are you getting these x values from? It doesn't matter. Choose any x values as long as they are less than or equal to 1. They satisfy this inequality, so you can use them. So I'll go ahead and plug those into the function so we can get some points out. When I plug -1 in, we have -3 minus 4, which is -7. When we plug in 0, we have -3 times 0 minus 4, that's -4. And when we plug in -1, that's going to give us a -1 back out. Okay, so I have some points that are on this graph now. I have the point 1, -7, I have the point 0, -4, and I have the point -1, 1. -1, -1. Now, when you're plotting these points, be careful with the points that came from the restriction. Remember that 1 showed up in the inequality? This is the point that came from the restriction. Now, we have to look at the restriction. The restriction says x is allowed to be 1, less than or equal to 1. So I know I'm going to put a closed point when I plot that point. When I plot 1, -7, I'm going to put some little markers in here to help me graph this. When I plot the point 1, -7, I'm going to be plotting a closed point. Okay? I don't have to worry about the points that did not come from the restriction, that didn't come from the endpoints, that didn't come from that number in the inequality. So the 0, -4, I don't have to worry about that. I know that's a closed point, definitely. The -1, -1, that's definitely another closed point. Okay? So I have those points plotted. Now, this is another part where people get tripped up in piecewise functions. They are unsure how to connect these 3 points. And what I mean by that is, do we just connect all 3 of them? Do we just connect them going on that way, downward? Or do we connect them all going this way, upward? And that's a very important part of graphing piecewise functions. To make that determination, go back to the restriction for your piece. Your piece says x is less than or equal to 1. Less than or equal to 1. Let's just think about the x-axis. We'll just put some more numbers on here, -1, -2, -3, -4, -5. And I'll put some numbers on my y's too, because we'll probably need them eventually. Okay, so x is less than or equal to 1. Think about where those numbers are on the x-axis. Here's 1. The numbers that are less than 1 are to the left. The numbers that are less than 1 are to the left. So when you connect those points, you need to make sure that that graph that you draw is ranging over the x values that are less than or equal to 1. You cannot connect these points and go that way. Because that way, if you go this way, you're hitting x values like 3, 4. Those aren't less than or equal to 1. And you can't connect those points and extend it on forever in both directions. Because that doesn't say less than or equal to 1. I can only go upwards, backwards, up to the left. Because I need to make sure that I'm ranging over the x values that are less than or equal to 1. And just to confirm that, I'll show you the graph that we had so far. Look at that red piece. The points we had were somewhere, say like here, the points that we plotted. We connected them and we went back upwards. Okay, ranging over the x values that are less than or equal to 1. Now let's look at the blue table. So I have x is greater than 1. I'll choose some more values. I'll just choose 2 and I'll choose 4. Just choosing some other values that are greater than 1. When I plug 1 into this function, we get out 1. When we plug 2, we get out 3. And when we plug in 4, we get out 7. So I'm taking these x values and plugging them in for this x right there. So just a quick example, I got this from 2 times 4 minus 1. I got that from 2 times 2 minus 1. That's where we're getting those values from. Replacing that x with those x values. So we are going to plot these points, the point 1, 1, the point 2, 1, and the point 4, 7. No, 2, 3. I was looking at the wrong thing. And the point 4, 7. But remember, we have to be careful with the point that we got from the restriction. That says x is greater than 1. 1 is not included in the second piece because there's no or equal to. So that point 1, 1, we will plot it, but it will be open. The point 1, 1, we will plot it, but it will be open. Okay, I don't know what that red point's doing there. Be open. So the openness signifies that it is not included. It is not included. It's included in the red piece. It's not included in the blue piece. And this is why it's important to make sure, even though it says x is greater than 1, that you're still putting that x value in the table. Because what I see a lot of the time is students will just go in and start the table at 2 because x is greater than 1. And I challenge that with, isn't 1.5 greater than 1? Isn't 1.0001 greater than 1? But if you start your table at 2, you've skipped over all those decimal values between 1 and 2. That's why you need to make sure you're still starting your table at 1. Okay, I'll plot the 0.23 and I'll plot the 0.47. And then I will connect those points ranging in the values, ranging in the direction of x values that are greater than 1. So when you connect these 3 points, head off to the right. Make sure you're only covering the x values that are greater than 1. And that's what the graph of this piecewise function looks like. Now that we have the graph of it, and notice the open and closed circles, okay? That's important. And you determine that based off of which inequality had the or equal to. The red inequality had the or equal to, it gets the closed circle. Now let's talk about the domain and range of this piecewise function. The domain is a lot more straightforward to find because you can find the domain without the graph. And one way that I find the domain is I make a number line. 1 is one of the numbers that shows up in the number line. I'll make sure that I put that on my number line. I'll just put some other numbers on it. And what I'm going to do is I'm going to look at those inequalities, those restrictions. The first inequality says x is less than or equal to 1. Less than or equal to 1. So it includes 1 and the numbers that are less than 1. So everything to the left of 1, all the numbers that are smaller than 1. And it takes the arrow too because it goes on forever less than 1, down to negative numbers all the way down to negative infinity. The second inequality says x is greater than 1. So it doesn't include 1, which is fine. It was included in the first piece. And it takes all the numbers that are bigger than 1. So everything off to the right of 1 all the way off to positive infinity. And then to get the domain, we read the shading from the left to the right. So the shading starts off at negative infinity. I can see that shading off the negative infinity in red. As we move to the right, everything is shaded. All of this is shaded. Sometimes people get nervous when they get to 1. Is 1 shaded? Yes. 1 was included in the red piece. So do not stop at 1. Keep going. It goes all the way past 1. That's when the blue piece kicks in. The numbers that are greater than 1, it goes off to positive infinity. So the domain is all real numbers. Negative infinity to positive infinity. Please do not generalize and say that's always the case. I promise in this series you will see examples where the domain is not all real numbers. Don't be that person that always says it's all real numbers. That's not true. Now let's look at the range. The range is a little bit trickier because to determine the range, you need to be looking at the graph. So I'm going to zoom into the graph of this piecewise function. Range deals with y values. So what y values does the graph cover? How I like to encourage my students to get caught up, because finding range from the graph, reading it off the graph can be a little tricky. So one hint that I use is, remember, we're talking about the y-axis here. Range is the y values. So what y values does this function cover? From the bottom to the top. So we're going to start down at negative infinity and work our way up to positive infinity. Pretend you're a tiny little ant. So this is you, tiny little ant, your antlers, and you're walking along the y-axis. And as you're walking along the y-axis, you're looking to the right and you're looking to the left, and you're asking yourself, do I see the function way out there? Do I see the function? When the ant is down here, moving up the y-axis, he does not see the function, because look all the way to the right, there's no function. Look all the way to the left, there's no function. It's not until he gets up to -7 on the y-axis that he sees the function, because he's going to see that little red dot when he looks to the right if he's at -7 on the y-axis. So the range starts at -7. And he does actually see the function at -7. -7 is included in the range. Because it is included, use a bracket. Because it is included, use a bracket. He's going to continue walking up the y-axis, looking to the right and to the left, and he'll continue to see the function once he gets past -7. He'll see the function. He gets up to 0, he still sees the function. When he gets to 1, sometimes people get confused because they look right and they see that open circle, which is not included. But when you look left, that red piece is included. So he's in the range all the way until he gets up to positive infinity. because he'll continue looking right and left and seeing either blue on the right or red on the left. So the range started at -7 and goes all the way up to positive infinity. That's the range of that piecewise function. So this concludes the second part. We're talking about the graphing and the domain and the range. And next we'll talk about the intercepts. So for the last part of this video, we are going to find the intercepts of this piecewise function, and we're going to do it algebraically. I get a lot of pushback from my students sometimes when I teach this because they say, if I have the graph, why can't I just look at the graph and find the x-intercepts? It's not always very straightforward to look at the graph and tell me exactly what the intercepts are, x and or y, and sometimes you might be asked to do it. If you're in my class, you can expect to be asked to do this. Okay, so let's start with the y-intercept. I believe we're starting with what's easiest, and the y-intercept is the easiest to find for pretty much any piecewise function. So just generally speaking, this is not even dealing with piecewise functions, this is just in general. You find the y-intercept by setting x equal to 0. Plug in x is equal to 0. That's how you find the y-intercept of any function, any y equals f of x function. Be careful here. This basically means to do f of 0, plug 0 into the function. I'll see people start plugging 0 into both pieces. You do not want to do that. You have to pick which piece do you use if you want to plug in 0. Which piece, which restriction says it's okay to plug in 0. X is less than or equal to 1, or x is bigger than 1. 0 is not bigger than 1. 0 is smaller than 1. So when you're plugging in 0, you need to be plugging it into the first piece of the function. So I'm going to plug in 0. So I have -3. I'm replacing the x with 0 minus 4. That comes out to give me -4. So the y-intercept of this function, depending on how you write this, is the point 0, -4. The x-coordinate was 0, the y-coordinate is -4. Some people just say the y-intercept is -4. I'm particular, I think intercepts are points, and so I write it as a point, but that's what it is. So on this graph here, there is our y-intercept that is at the point 0, -4. Okay? And I think, in fact, yeah, we even saw that up here from our table when we plugged in 0 and we got out -4. Notice we did not use the blue piece. Why did we not use the blue piece? Y-intercepts only happen when x is 0. A graph is only going to touch the y-axis. Any graph is only going to touch the y-axis when x is 0. That y value could be anything, 3. So I was not allowed to use that second piece because the second piece only exists when x is greater than 1. But I need to plug in 0. Okay, so when you're finding the y-intercept for your piecewise function, you're only using, there's only one piece you could possibly use. Sometimes there might not be a piece, we'll look at more examples later, but there's only one piece you could possibly use, and it's the piece that includes 0 in the restriction. And if the function is written correctly, you'll never have a piece, more than one piece that includes 0. Okay, again, violation of the vertical line test, but anyways, I digress. Now let's talk about the x-intercepts. Clearly, we can look at the graph. I have a little printout of it right here because mine is all marked up from the range and the ant. But clearly, I can look at this graph and see this graph only has one x-intercept right there, and it's coming from the red piece. But I wouldn't know that if I didn't see the graph, right? I wouldn't know that automatically. It wouldn't be so obvious if I wasn't looking at the graph, because the blue line will eventually hit the x-axis if I extend it, but we didn't have that piece. So that the blue piece isn't giving us an x-intercept. So I want to show you how you can understand that algebraically. In terms of finding x-intercepts, you set the function equal to 0. That is always true in general. For x-intercepts, you set y equal to 0. A function will only have an x-intercept when the y-coordinate is 0. So that means set the function equal to 0. So I'm going to set both pieces equal to 0. The function has two pieces. It has the red piece, and it has the blue piece. And I'm going to solve both of these equations. Solving the red equation, I'll add 4, -3x equals 4, x equals 4 over -3, -4/3. Solving the blue piece, add 1, 2x equals 1. I'll divide both sides by 2. X is equal to 1/2. Now this is where we have to be careful, because I can't just say that both of those are x-intercepts, and in fact, we know that both of them are not x-intercepts. Right? There's the graph right there. Those are not both x-intercepts. The red piece gave us negative 4/3. But remember, the red piece only exists when x is less than or equal to 1. This is where 1 is. This is where the graph splits. Is negative 4/3 less than or equal to 1? Yes. This is less than or equal to 1, so that works. It will be on the graph. We can see it right there. That's the point, negative 4/3, 0. Don't question that minus, okay? Negative fractions, put the negative in the front, in the top, in the bottom, anywhere you want to write it, it's the same fraction. So we do have an x-intercept at the point negative 4/3, 0. That is an x-intercept. Let's look at that blue value. Blue, we got a half. That means the blue line is going to hit the x-axis. If I extend that out, it'll hit the x-axis at the point 1/2, 0. But that wasn't on our graph. Right? I drew that in. That was not on the graph. And it wasn't on the graph because the blue piece only exists when x is bigger than 1. 1/2 is not bigger than 1. So that x value of 1/2 does not give us an x-intercept because it does not fit into the restriction for that blue piece. It doesn't exist, not on our function. And so that is how you find intercepts of a piecewise function algebraically. I hope you have found this video helpful. I know it was just one example and still a little bit on the longer side, but it's the first in a series and I want to make sure that you have a very good understanding of piecewise function. Every time I teach piecewise functions, there's always some confusion. It's not an easy topic, so I wanted to give you a very thorough breakdown and explain what's going on. If this video was helpful, please do give it a thumbs up. If you had any questions, feel free to comment them. I'll do my best to get back to you. I'll see y'all next time.